difference between combinations and permutations is that order is not important. Not important for a combination. I always go back to the food example when I think about combinations. I love Chipotle. So I go to Chipotle and I tell them I want, you know how they always ask you if you want rice and beans and whatever. And so you pick rice and beans. Well, what if they put the beans on first and then the rice? Or what if they put the rice on first and then the beans? Does it really matter? No, you can just flip your burrito around, right, and eat it the other way if you really care. So it doesn't really matter which order that they put it on. That would be a combination problem when Chipotle advertises and they say we have a million ways you can select burritos. They're doing combinations. They're figuring out how many choices, how many ways you could pick the items from Chipotle. So I like the food example. Now, what's the difference in this formula for combinations versus the formula for permutations from yesterday? R. This extra R factorial on the bottom, right? Was not there for the formula for permutations. Now, most of the time you're going to be using your calculator, right? And you're punching this into your calculator and you're coming up with an answer. But it's important that you know what your calculator's doing, why it's getting a different answer than it was with the permutation. So it's going to take that extra R factorial on the bottom. I like the food example. The book uses cards a lot. They talk about poker hands and how poker hands are combinations instead of permutations. So think of how many of you have played poker at some point in your life? Oh, only about half. Okay. Well, so you have 52 cards in a deck, okay? And you're sitting around with a bunch of people and you're dealt 5 cards for a poker hand. Let's say that I got an ace. Does it give me a different hand if I got an ace of hearts first or if I got an ace of hearts last if I had the same other 4 cards? No. So this is a combination problem because it doesn't matter what order you're dealt the cards. It just matters the combination of 5 cards that you get at the end. Okay? Combination problem. All right, so our first problem here. If the order that they're dealt is not important, how many different 5-card hands are possible? Well, how many cards do you have to pick from? 52. And you're picking how many? 5, right? We're dealt 5 cards. And so you guys find it on your calculator. It's the same spot as a permutation. And the answer's not important. Check in with your neighbors and make sure they have the same answer as you do. It's just that you know where to find it. Now, how many of you played Texas Hold'em? Anybody played Texas Hold'em? Yeah, a few of us. So if you haven't played Texas Hold'em, what happens is you get 3 cards, and then I don't know exactly how it works, but you guys help me out. They flop over a couple cards. Okay. Okay, so you get 2 cards, then they flop 3 cards, then they give you another card, right? And then they flop another one. And so the idea is order is more important in a situation like that because you're betting as you're going. And if you don't feel like you have anything at first, you're not going to bet. Whereas if you get 2 aces right at first, you're definitely going to bet. Okay, so different type of situation. So I don't want you to always think that card, when you're playing poker or different kinds of poker, that it's always a combination. You have to think situation to situation. Okay, so second one. This one's a little bit trickier. How many 5-card hands are there that all 5 cards are going to be of the same color? Well, how could that happen? What could be in my hand if that were to happen? I could have 5 what? I could have 5 hearts. Would this be the same situation if I had 3 hearts and 2 diamonds? Would that fit? Yeah, because those are the same color, right? If I had hearts and diamonds. So let's say that I wanted a hand of red, hearts or diamonds. Doesn't matter. How many cards do I have to pick from? 26. And how many am I picking? 5. Picking 5. This, if you plug this in your calculator, would tell you how many hands you could have with all red cards. how else could I get a hand that's all the same color? Black, right? So I want all black. Meaning that I could have either spades or clubs. By the way, how many are there of each suit? 13. These are important things that you're going to need to know in order to be successful this chapter. There are 13 cards in each suit, 52 cards total for a deck. So how many black cards do I have to pick from? 26. And how many cards would I want in my hand? 5. This is, and we're going to on the next slide see that this is an or situation. I can't have red and black. And anytime that it's or, it's either red or black, I'm going to add. And so another way to look at this, I could multiply this by 2, since those are both the same, and get the same answer. And again, I'm not going to worry so much about the answer because you guys can just punch that into your calculator. It's more the process. Questions on that one? Okay, so here's our rule that you have to follow. Whenever it's and, you're multiplying. Whenever it's and, you're multiplying. Whenever it's or, you're adding. Okay, so the book gives all kinds of these card examples. I'm going to go back and give you another one because I feel like theirs are a little harder than some of these were. So let's write this one down. Let's say that you still had 5 cards total for poker, but we need a hand that is 1 king and 4 cards other than a king. Okay, 1 card that's a king and 4 cards that are other than a king. You're going to be really successful in this if you can figure out how many you have to pick from and how many you're picking. So let's separate this into 2 problems. Let's just do the king part first. How many kings do I have to pick from? 4. And I want how many? 1. 4C1. Okay? Now I'm going to do this other part separately. How many cards do I have to pick from that are cards other than kings? 48, because I have 52 minus those 4 that we were just talking about. And how many am I picking? 4. Okay, now, question to think to yourself. Are we having 1 king or 4 cards that are not kings? Or are we having 1 king and 4 cards that are not kings? And, because I need 5 cards total, and means that I do what? Multiply. Okay, so you'll see lots of problems on your homework like that. And again, you guys can do that on your calculator. Questions on that one? I'm going to let you guys read through these and see if you can figure these 2 problems out. Okay, let's look through the first one. All right, so you're picking plays to read, and you have to read 2 comedies and 1 tragedy. So let's deal with the comedies first. How many do I have to pick from? 18. And I'm picking 2. 1 tragedy. I have 10 to pick from, and I'm picking 1. Do I add those or do I multiply? Multiply. And you should, if you put that into your calculator right, get 1,530. Okay, if you didn't, you may want to check with the neighbor and see what they did differently. Okay, part B. This one's definitely trickier. At most 3 plays. Your teacher tells you you should read at most 3 plays. What would satisfy that? What would be okay to read? 1, 2, 3, none. Okay, so we have 0, number of plays, 0, 1, 2, 3. Can you read 0 and 1 and 2 and 3? Or is it an or? 0 or 1 or 2 or 3. It's an or, right? So I'm going to have plus in between each of these. Okay, of total plays to pick from, we have 38. So 38, and I would pick 0 for that first option. How many ways are there to read 0? 1. That's always going to be 1 whenever you have a 0 there. Okay? Or I have 38, and I could pick 1. How many ways would there be to do that? 38. Yep. So some of these we can figure out without even using our calculator. Then I have 38, and I'm picking 2, and 38, and I'm picking 3. What if the problem said at least 3 plays? What would satisfy that? Close, 4 through 38. At least 3 plays, 3 through 38. So you'd have to do one of these for each of those numbers, 3 through 38. That seems like a lot, right? In that case, there's actually an easier way to do some of those. You can subtract off the possibilities that would not satisfy your situation. Okay, so instead of doing that problem, let's look at this basketball problem instead. Read through this one. So in this problem, if we wanted to attend at least 3 of the games, that's like the same situation that we were just talking about with the plays, reading at least 3. We could go to 3 or 4 or 5 all the way up to 12, right? Because there's 12 home basketball games. If we subtracted off the opposite of that, we subtract off going to what wouldn't satisfy this? 3, 2, 1, 0. So if I went to 3 or 2 or 1 or 0, which is a lot less possibilities than adding up all the ones that are going to work. The really tricky parts of this is figuring out the total possibilities, I think. Okay, so you have 12 basketball games. How many ways could you choose to go or not go to these 12? Well, let's just kind of make a little chart here. So these are all my basketball games. And I'm going to pretend that that goes out to 12. I could either go to the basketball game, or I could not go to that first basketball game. So how many choices do I have just for the first one? 2. For the second one, I could either go or I could not go, and so I have 2. And on and on and on. This is a counting principle problem. I have 2 ways that I could either go or not go to each of these basketball games. All the way up to 12 total basketball games. Can I simplify that? 2 times 2 times 2. 2 to the 12. That's how many total ways I could go or not go to the basketball game. We need to know that in order to be able to subtract off from it. That's the first part. This part of subtracting off, that's not quite so bad. So I have 12 games to go to. I could pick 3 to go to. Or I have 12 games to go to and I could pick 2 to go to. Or 1 or 0. Bless you. So I'm subtracting off the ways that do not satisfy the situation that I'd want. And again, I'll let you guys do that on your own on your calculator. Oh, you're totally right. Thank you. And at least 3 would count 3, right? So I should only have the 2, 1, 0. Thank you. Good call. Other questions? Read through this one. this problem look familiar to you? If you look back to the warm-up problem that we did, it's exactly the same except for, I think, one word. Same. And in the warm-up problem, it said different. Okay, so let's go back to these 4 people over here in this group. 50 raffle tickets, right? These 4 over here win. We know that they're going to win for sure. It's rigged. I don't know. Let's say that they're each going to win $50. Now do they care so much about which order they're picked? If they're picked first or they're picked last, if they know they're going to win $50 no matter what? No. Doesn't matter, right? And so this is not a permutation situation anymore like it was in the warm-up. This is a combination situation because of the prizes being the same. So I still have 50 people that I'm picking from. I still have 4 that I'm picking. But this is going to be a combination situation. Questions? Should this be more or less than the previous? Let's think about the formula again. The formula for this would be 50 factorial over 50 minus 4 factorial times, here was the difference, right? 4 factorial. This is my n, this is my r in the formula. What your calculator did in the warm-up was without that. Is this going to be more or less? Less, because you're dividing by an extra number, right? Less ways to make that happen. All right, that's the first part of the homework. Second big idea is this. Read through that little description of Pascal's triangle. Way back in the 1600s, a mathematician figured out that if you organize these ways of combinations, it made this really unique type of triangle. Okay, so what he did was he figured out what would happen if I had 0 to pick from. Okay, 0 to pick from and I pick 0. Well, there's one way to do that. For the next row, what if I have one choice to pick from? Well, I could either pick 0 or I could pick one of that one choice. Okay, so we figured out each of those, and that's the second row. Or it's called the first row, sorry. Second row here, so I have 2 choices to pick from. I could either pick 0 or 1 or 2. And he labeled he put all these numbers out here. And it made this really cool pattern where the first number in the row was always a 1. And the second, or the last number in the row, again, is always a 1. But you could get the numbers in the middle by adding the previous together. So 1 plus 2 is 3, 2 plus 1 is 3. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. Okay, so this is handy for a couple different things. One, let's say we didn't have a calculator and we wanted to figure this out, which if any of you are ever taking the AccuPlacer, part of that you can't use your calculator. I think that's the only test that I know of you can't. But we could figure out, what if we had 6 choices? Well, you guys figure out the 6th row for me. Add it onto your triangle. Figure out the 6th row. So this kind of seems confusing at first, but really it's a piece of cake. Your first number is always going to be a 1. Your last number is always going to be a 1. And then to find all the digits in the middle, you just add up the 2 numbers above the one that you're looking for. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. And so on. Okay. So if you were doing the AccuPlacer or for some reason didn't have your calculator with you, you could use Pascal's triangle to help you figure out a combination problem like this. So without using your calculator, answer this question. So the idea behind this is you have 6 people to choose from, and you're choosing 2 to be in a group to go to this convention, right? So it's 6C2. The order that I choose these people doesn't matter. So I can use Pascal's triangle. I have to find the 6th row, which you guys just found. And the first entry in that row is going to be 6C0. And then they go in order, 6C1. And so our answer to 6C2 should be 15. Plug it in your calculator and see if it is. 6C2. So that's one use of Pascal's triangle. I don't know that you'd use that a whole lot, because how many times don't you have your calculator, right? But I think this is really cool, is if you had a problem like I have on the board here. A plus B to the 4th. That means A plus B times A plus B times A plus B times A plus B. And if I were ever asked to multiply this whole thing out, which sometimes in upper level math you are asked to multiply something crazy like this out. Well, I went through and did it, and I had to erase several times because I made mistakes along the way. And my answer ended up being this. How many of you think you could probably do that first try and get it 100% right? There's a lot of places you could make an error, right? And we probably could do it, but we might make an error along the way. Well, we can use Pascal's triangle and the binomial theorem to skip all of the work in between there. Okay, so we just talked about Pascal's triangle. What the heck is the binomial theorem? That's this crazy thing down here on the bottom. This really isn't as bad as it looks, so don't freak out about this, okay? So I just did A plus B to the 4th power. And all of this notation is kind of confusing, but the idea behind this is you have one term and you have a second term. You have a binomial, okay? 2 terms. And in our answer here, we're going to have each of those terms. I have A, and this one really has an A as well. This is an A to the 0 power. Okay? And I have a B in each of these. This one doesn't show it, but it is a B to the 0, and B to the 1st, and B to the 2nd, and B to the 3rd, and B to the 4th. What the binomial theorem tells you is that you're going to have both of those terms, the A and the B, in each term in your answer, but one of them is going to start with the biggest exponent of 4 and go down, A to the 4th, A to the 3rd, A to the 2nd, A to the 1st, A to the 0, and the other one's going to go up, B to the 0, B to the 1st, B to the 2nd, B to the 3rd, B to the 4th. Okay? Combining that then with Pascal's triangle, we had a 4th power here. I'm going to flip back to the previous slide. 4th power, or sorry, not 4th power, 4th row, 1, 4, 6, 4, 1. Notice our, I can get this to come back up. 1, 4, 6, 4, 1. Okay, that is in the binomial theorem here. Those are our combinations. That's the piece of Pascal's triangle. Okay, so again, a lot of notation. Let's actually do a problem because it's way easier if we just jump into this. Okay, so here we go. Our first one here. So we have a 5th power. What I want you to do right now is go back to Pascal's triangle and find the 5th row. Now remember that it starts with row 0. So count down 0, 1, 2, 3, 4, 5. Everybody got it? Find the fifth row in Pascal's triangle. Okay, so the fifth row is this. 1, 5, 10, 10, 5, 1. If you don't see that, talk to your neighbors right now and find that on Pascal's triangle. This is the fifth row starting with 0. 0, 1, 2, 3, 4, 5. That's going to be, those numbers are going to be the coefficients of all of our terms if we had multiplied this whole crazy thing out to the fifth power. Okay, in each of these, we're going to have an x and a 3. Okay, always start with your first term here. Let's do the x. So I'm going to put an x in each of these. And we're going to start with our highest exponent. So we have to the fifth power in our problem, the first term is going to be x to the fifth. From there, you're going to go down. So the second one's going to be x to the fourth, x to the third, x to the second, x to the first, x to the 0. Okay, then we're going to plug in our 3. I'm going to put a 3 in each of these, and it's multiplication here. Now these don't go down, these are going to go up. So our first one is going to be 3 to the 0. Then 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth. Okay, these are each terms, so I'm going to put a plus in between each of them. One hint to this too, if you're ever like, I'm not sure if I put my exponents in right, what do you notice that your exponents all add to? They all add to 5 in this case, which is the exponent on our binomial, right? That should always happen. If it was a 6 up there, they should add to 6. Now we just have to simplify. Okay, so 3 to the 0 is what? Nope, 1. So I'm going to get rid of that because if I multiply by 1, that really doesn't change my problem at all. So 1 times x to the fifth, that's just x to the fifth. Plus, okay, we have to simplify the number part. So I have 3 to the first, which is 3, times 5 is 15. So this one's going to be 15x to the fourth. Next one, remember you always have to do this exponent first. So 3 squared is 9, times 10 is 90. You guys keep going. You finish the problem. Okay, let's finish this up. So 3 to the third is 27 times 10 is 270. 3 to the fourth is 81 times 5 is 405. 3 to the fifth is 243. What's x to the 0 again? 1. So 243 times 1 is 243. I don't really need that x to the 0 there. And so this whole thing is your answer. That is what you would get if you multiplied out x plus 3 times itself 5 times without all the extra work behind it. So question was, will this be on the homework? Yes, it will also be on the quiz and the test. So you can't say this is too hard, I'm not going to do it. You all can do this. Okay. We're going to do one more of these. Let's see, which one do we want to do here? I'm just going to give you a hint on this one, and then we're going to skip down to the last one. This is always the sum. This formula only works for the sum of a binomial. So you would, in the second problem here, have to change this to addition, and your last term would be a negative. Okay? So as you're going through, you would have, using parentheses, negative 2b to whatever power it is. Okay? I do want to do the last one, though, just because of this squared, because that makes it a little bit tricky, too. Okay, what is the exponent on the outside of our binomial? 3. Okay, you guys find the third row in Pascal's triangle and write it down. So hopefully you found that it's 1, 3, 3, 1. Okay? Now, our first term is x squared. This kind of throws people off. So I have x squared, and I'm going to put parentheses around that, in each of my terms. The first one is going to be x squared to the what? Third. That's our exponent on the outside. X squared to the third, to the second, to the first, to the 0. Then I have the y, so let's put that in each of them. So what should the first one be? Y to the 0. And then it goes up. So y to the 0, y to the first. Put your plus signs in there. Okay, so let's simplify this then. What do I do if I have an exponent to an exponent? Multiply. So this is 1 times x to the 6 times y to the 0. The y to the 0 I can get rid of. You guys keep going. Okay, check your answer. Now, just to point out, in this problem, my rule doesn't hold true, where you can't add your exponents together to get the 3 on the outside, and that's because of the 2 on the inside. Okay, if you went back to the step before, these numbers would all add to your 3. Are we all going to do binomial theorem? Yes, each and every single one of you are going to help each other with binomial theorem.